Hello, everybody. This is Andreas Hugi and Marcus Mangold. So we'll give you today a webinar on pushing the frontiers of biospectroscopy with the IRis-F1. The presentation will be held by Marcus Mangold. He has received his master in micro and nanotechnology in Uni Basel. Then he moved to Germany to do his PhD in physics in the TU of Munich. Afterwards, he moved to EMPA, where he worked the first time with QCL for high-sensitivity trace gas sensors. Afterwards, he was a co-founder with me of IRis-F1 and is acting now as a CTO. And I'll give the stage to you. So please tell us the latest news on biospectroscopy with the IRis-F1.
Thank you, Andreas, very much for this introduction, and welcome everyone to today's webinar. So we are going to talk about the IRis-F1 and how it can be used for biospectroscopy. Let me give you a brief overview on what this webinar is going to be about. First, there will be a presentation of the spectrometer, the IRis-F1 itself, and its special features, especially with respect to biospectroscopy. Then I would like to introduce you to the modular construction of it with its laser modules, and I'd like to introduce our latest addition to our wavelength portfolio, a laser which nicely covers the Amide 1 band of proteins. Then we go through 3 different applications that were proven with the IRis-F1. The first one will be in process analysis in the pharma industry, where we show how the IRis-F1 is useful for measuring optically very dense samples. The second one will look at rather slower reaction kinetics, or what we call slow in a polymerization reaction. And then we will look at the very fast reaction kinetics, which are used for optically active proteins. So here you get a first view of the IRis-F1. On the left-hand side, you see the spectrometer. From the outside, it looks pretty much like a standard infrared spectrometer. It has this big red door to the right side, which is the sample chamber, where the user can put his experiments or where he can couple out the light to use somewhere else. Now, the outside looks very standard, but on the inside, it has some very special features, and they are best summarized with those 3 keywords that are mentioned here. It has high speed, high brightness, and parallel multi-wavelength acquisition. What that means for you as a user is high speed lets you measure very fast processes. So if you're interested in any kinetics, typically of chemical reactions or biochemical reactions, then you can follow those with the high speed of the instrument. Alternatively, the high speed can also be used to measure many samples in a short time, and that is useful if, for example, you think about point-by-point rasterizing an image, so a hyperspectral image, or if you want to do high-throughput analysis. The high brightness is very useful when you are working with very strongly absorbing samples, and that is especially in biospectroscopy often the case because water is a very strong absorber in the mid-infrared, and if you want to measure your samples in the watery environment, you often happen to work with strongly absorbing samples where the high brightness helps. And finally, the parallel multi-wavelength nature of the instrument allows you to measure complex mixtures or observe multiple bands changing in your process. Now, I would like to give you a very short technical introduction. I know this is probably going to be a bit too short for you to really understand the technical basis. So if you want to know more, I advise you to look at our former webinars or browse the technical section of our website. But I'd like to point out the key features inside. So what is the really big change in our spectrometer is that it's a dual frequency comb spectrometer. So as a light source, it doesn't use a glow bar as standard infrared spectrometers, but it uses those frequency comb lasers. They are arranged in the instrument in assembly as shown at the top right of this slide. you have those two frequency comms, that's why it's dual frequency comm, and they are superimposed on a beam splitter, then sent through a sample, and then detected by a detector. Now, what happens if you overlay those two frequency comms? Well, maybe before we do that, what is a frequency comm? A frequency comm is a laser which emits not only one wavelength, but it emits many wavelengths at once. Now, if you overlay two frequency comms, you get an optical spectrum as shown in the top graph here, where all the blue lines belong to one frequency comm and all the red lines belong to another frequency comm. And now comes the somewhat complicated part. When you mix those two lasers, you will start have a beating between pairs of those lines. So each blue line has its corresponding red line, and together they make a beating at a radio frequency, which we can measure with standard electronics. And that is the whole magic, how we can measure many, many wavelengths of this laser in one single measurement in a very short measurement time. So the key take-home message from this slide is the difference between our spectrometer and standard spectrometers is that you have laser sources, and those lasers have multiple wavelengths, which we can measure in a very short measurement time in parallel. So, and this is what you finally get out if you do a measurement with an IRis-F1, and here you also get an idea of what we call fast. So typically you get this 3D type of plot when you measure something. One axis here is the wave number axis. That is the spectrum that you cover with your laser. Typically that's somewhere between 60 and 100 wave numbers. And then you get this spectrum every 1 microsecond. So, and you get this continuously for several milliseconds. And that's how this surface plot appears that you can see here. So what you can see is really the spectrum evolving over a time of several milliseconds with microsecond time resolution. Of course, also longer timescales are accessible, and I will show you that later in the application examples. Talking about brightness, I'd like to compare the IRIS to conventional infrared spectrometers. If we're talking about an FTIR as available from the big companies Bruker, Thermo, Agilent, they use a glow bar light source, so a thermal emitter, and those have rather limited light per wavelength. So what you get out of such a light source is typically 10 to the minus 15 watt per hertz. If you use a laser, you get many orders of magnitude higher in the intensity. So our laser, as well as alternative laser products as for example external cavities as available from daylight or block engineering, they have spectral brightness on the order of 10 to the minus 9 watt per hertz. Now, what further differentiates us from other laser techniques is the high speed, which is plotted on the bottom axis on this plot, and that's really the unique combination of the IRis-F1. We got this high brightness and at the same time the high measurement speed of 1 microsecond per spectrum. And finally, there's the parallel multi-wavelength acquisition, and here you finally get to see something like a measurement. That is what we really detect in the instrument. You see all those multiple lines. Each of the lines that you see in this graph corresponds to a laser emission line, and the laser here covers around 70 wave numbers. Typically, they are somewhere between 60 and 100 wave numbers, and all those lines are measured in parallel. Now, you may say 60 to 100 wave numbers is enough for one experiment, but different experiments need different wavelength ranges. And therefore, I'd like to show you a feature that we implemented in the spectrometer. Here again, you see the IRis-F1 spectrometer. On the right-hand side is again this red door, which is the sample chamber, but now we've also opened the left door, inside which we have those exchangeable laser modules. On the table, you see one of those laser modules, and these laser modules contain the two frequency comm lasers and all the optics which is needed to combine those two lasers. So the output of such a laser module is already a pre-aligned, pre-combined dual frequency beam, and that makes it extremely easy to exchange your lasers in your instrument. And I promise you, if you just lift up that laser module, plug in the other laser module, within a few minutes, you are in a different spectral band, and you can measure your experiments at a different wavelength range available by a different laser. Let's now look at what a given laser actually can do. And for the audience here, I have picked a laser which covers the amide 1 band of proteins. The amide 1 band, as you may know, is very specific in protein measurements because it is highly specific to different secondary structures of proteins. So looking at the shape of your amide 1 band, you can say how much alpha helix, how much beta sheet, or how much random coil or other secondary structures you have in your protein. Now we have developed a laser which is exactly centered at 1650 wave numbers, which is also where the amide 1 band is centered. It covers a bit more than 70 wave numbers with a wavelength spacing of 0.3 wave numbers. So like this, you get to measure a spectrum of this amide 1 band with several hundred measurement points in a single acquisition. Let's look at the spectrum a little bit more closely. So here you see it again. You can see we have all those red lines, but some of them are actually missing. There's holes in that spectrum. Now, those holes are not actually missing lines from the laser, but around the amide 1 band, we also have very strong absorption features of water. So if we now compare this to a calculated spectrum of water vapor, then we can see that everywhere where we have a missing line, that is because this line is absorbed by strong water. Of course, if you use that module in the instrument, you can purge your instrument and you will get back those lines. But having those lines here helps us to actually accurately assign the various lines to their wavelengths, and from that we can get what is shown on the bottom graph where we see with what signal to noise ratio we can measure a spectrum at what wavelengths with this laser. As you can see, the laser emits from below 1680 wave numbers to above 1610 wave numbers. That's more than 70 wave numbers of coverage. And it has an excellent signal to noise ratio on the order of a few milliOD in 100 microseconds in most of the wavelength range, roughly from 1675 to 1610. And I think with this laser, it is really possible to look at very small changes of your secondary structure in time-resolved measurements with this module. So let me quickly summarize the specifications of the IRis-F1. I hope I have shown you now that we have as a light source those quantum cascade laser frequency comms in exchangeable laser modules. Each laser module emits around 50 to 100 milliwatt of optical power, and it covers more than 60 wave numbers per module. Then center wavelengths, we didn't go into that so far, but center wavelengths are available roughly in the range 5 to 10 micron or 1000 to 2000 wave numbers. Spectral resolution is a somewhat complicated topic in dual measurement because you actually have an extremely high spectral resolution on the order of 10 to the minus 4 wave numbers. That's the width of your lines. But for everyone doing condensed phase measurements, what is more important is the spectral sampling, so how often you have a measurement point, and that is somewhere between 0.16 and 0.5 wave numbers. So typically you get a measurement every 0.3 wave numbers, which for all condensed phase spectra is an excellent spectral resolution. And then, of course, there is the time resolution, which is important. You can get down to below 1 microsecond time resolution with noise properties of 10 milliOD at 10 microsecond integration time and below 1 milliOD at 1 millisecond integration time. Okay, that was all about the introduction of the IRis-F1. Now I'd like to show you some applications which we've proven with this instrument. There's a whole bunch of interesting applications that can be where the IRis-F1 can be used for. I will not go through all of them which are mentioned here, so I will not go through the bottom row, which contain photochemistry, where people look at optically induced chemical reactions, or combustion research, where people are actually interested in the combustion of fuels, mostly also with respect to those new biofuels, where you have to understand how they burn, and all those things happen on very short timescales. Another measurement where we get a lot of traction is trace gas analysis or general high-resolution spectroscopy, where people are mostly interested in the high-resolution feature of the instrument. Now, today I will concentrate on the top row of the measurements, which is the process monitoring in pharma industries, polymer chemistry, and protein kinetics. So let's start with this process analysis in the pharma industry. Here we were approached by a customer who said they have a problem that they want to detect a small molecule drug dissolved in water. Now, the problem which they had is they were doing it so far with FTIR, but they could not reach as low concentrations as they wanted to. So what they could measure with the FTIR was about 2 milligram per milliliter, but the target concentration to measure was actually 0.1 milligram per milliliter. So there was a factor of 20 missing in their measurement precision. Now, one possible solution to such a problem is to just go for a longer interaction path between the analyte and the light. But to do so, you have to pass through a thick sample of water. And that is very quickly a big problem if you try to do this with an FTIR, because the water absorbs very strongly. But of course, us with the laser source, we could do that. So we set up an experiment, as you can see on the picture here. You see a single pass transmission cell here. That is a commercially available transmission cell from SpecAc. And we pass our laser beam through it. We have spacers there which make the optical pass 100 micrometer long. To compare that with an FTIR, you would pass through a maximum of about 5 micrometer of water sample. And here you can see the actual measurements. The top left is the bulk absorption and the actual problem that you have if you try to do this with a glow bar light source. Because as you can see, the bulk absorption is more than an OD2. So just the water in the sample absorbs more than 99% of our light. But with the laser, we still get some light at the end of this. And if we subtract that water matrix, we are at the bottom left graph, where we can clearly see the dissolved aspirin in the water. Here you see a concentration series, which ranges from 3 milligram to 0 milligram per milliliter. And you can already see in that bottom left graph that we can certainly see more than 2 milligram per milliliter. After a baseline correction, the measurement looks at the top right, and we can clearly see this absorption feature, which linearly scales with the concentration of the aspirin in the water. And then at the bottom right, we actually plot this concentration, the absorption that we measure as a function of the concentration, and you see a very nice linear dependence. And we determine from this measurement precision of 0.5 milligram per milliliter. And with this, we could well achieve the aimed at 0.1 milligram per milliliter. Now, as a summary of that, the main take-home message of that is you can actually do accurate transmission measurements with the IRis-F1 even if you have a matrix which absorbs more than 99% of your light. And this allows you to do your measurement in thicker samples, which has several advantages. One is you get a stronger signal because you are working with thicker samples, but maybe even more important for your daily routine in the lab is that this greatly simplifies your sample preparation. And especially if you think about working with flow cells, that makes your sample handling much simpler because you need much lower pressures to pump your sample through your flow cell, and it prevents clogging of your analyte in your flow cell. The next example I'd like to show you is not so much of a biological application, but it was brought to us by Delo Industrieklebstoffe, a company which, among other things, produces UV curable glues. Why I want to discuss this here is because it very nicely shows how you can span all different timescales which can appear in your experiment, starting from microseconds up to very long measurement times. So the problem that Delo had when they came to us is that they are developing new UV curable glues. And of course, their customers want those glues to cure very rapidly. So they develop them to cure very rapidly. But then they could not follow the curing process anymore with standard FTIR spectroscopy, which they used before. So they needed a faster measurement, and they asked us if we can do that with the dual comb spectrometer. Now, before we actually go to the measurement, I'd like to point at different measurement modes and the advantage which they bring for this measurement. So if you do a standard measurement, or the standard measurement type in the IRis-F1 is a time-resolved measurement, which is displayed in the top row here. What you see there is at some moment, your experiment sends a trigger to the spectrometer. That is where your experiment starts. Typically, you measure some pre-trigger samples, which act as your background. And then you continuously measure your spectral change with microsecond time resolution up to 32 milliseconds. And then this you can do again and again if you repeat your measurement with some given acquisition frequency. That is what we call the time-resolved mode, but there's a second mode which we call the static measurement mode. It works similar. You also measure in a standard configuration up to 32 millisecond samples, but then you average all of those spectra together and get one spectrum of your 32 millisecond measurement. And then this first spectrum acts as your background, and then the following spectra act as your sample measurement, where also you average all the spectra over your complete acquisition time. Now, 32 millisecond is the default measurement length, but you can actually upgrade that to 256 milliseconds. And the point that I want to make here is that this will allow you to actually look at all the timescales which are present above microseconds. Because if you now also make your first measurement shorter, for example, you go to static mode, but you only take 1 millisecond measurements and repeat them every 40 milliseconds, then you have the 256 millisecond continuous measurement of the time-resolved experiment, and every 40 milliseconds your static mode experiment, and like this you can access all the timescales from the microseconds up to as long as you want. Now, let us see what that actually looks like in an experiment. Here you see the setup that we built for that experiment. We have used an attenuated total reflection configuration for that measurement. Also here we use a commercial ATR crystal from SpecAc, the Golden Gate. And there we put a drop of this UV curable glue on top of the crystal. And we have a UV lamp, which is guided there by fibers. And when we start this UV lamp, all you can see by eye is blue light appearing and some smoke appearing. But if you look at it in the infrared, you see a little bit more. here, that is the offline measurement, so a measurement long before curing. You see there is a strong absorption maximum at 1648 wave numbers, and then after curing, there is an absorption the one at 1648 is disappeared, and there's a new absorption maximum at 1635 wave numbers. Now, if you do our static mode type of experiment, that is what is shown here. So what you see here are spectra measured with 1 millisecond integration time every 40 milliseconds. And you clearly see how the spectrum evolves from this maximum at 1648 wave numbers, which disappears, and a buildup of a new maximum at 1635 wave numbers. I'd like to point out the excellent signal quality here. So you see we have those milli-OD of signal of measurement noise in a measurement which only takes 1 millisecond of integration time. Then at the bottom right, we actually plotted the kinetics, so how those two peaks evolved. And when we try to fit that, we see that there is some second order kinetics needed to describe that process. And that's the point where we give the information back to DLO, because that is what they can use to optimize their curing process. Now, that was the kind of slow kinetics here. Let's also look at the fast measurement. So here we went to time-resolved measurement mode and did the very same experiment. You can see now here spectra taken at a few milliseconds after starting the UV lamp. So first we have the pre-trigger time, -3 to -0 milliseconds, and you see that is our reference, so we have 0 absorbance. Then we clearly see how the one peak disappears around 1650 wave numbers, while the other peak around 1630 wave number appears. But actually having the very high time resolution gives us even more new information, because if we look at the spectra, at the first spectrum from 100 to 500 microseconds, the light gray curve, then we see that there's not only one bump, there's actually 2 bumps there. And this is not noise, that is very reproducible through many measurements, and it actually points at an intermediate species. And this even more is the kind of information that the chemists need to optimize their curing, and at that point we leave it to them what to do with the information. So I hope I could show you with that experiment that the IRis-F1 can actually nicely cover all different time scales, from the microsecond range up to several milliseconds, or well, hundreds of milliseconds, or up to minutes actually, if you work in static mode. So let's get to our last example, which is protein reaction kinetics. And this is shown at the example of the bacteriorhodopsin photocycle. Bacteriorhodopsin is a membrane protein which is found in some bacteria, and it's one of the simplest photosynthetic machines in the world. So what happens if you excite this protein with visible light is that it pumps a proton from one side of a membrane to the other side of a membrane, and by this builds up chemical energy. Now, if we look at what really happens in detail, we see that this protein runs through a bunch of states which were named K, L, M, N, and O state. And all those states have different lifetimes in the range of a few microseconds to many milliseconds. Now, nicely enough, all of those state changes can be followed by infrared spectroscopy. And that has been excessively done with StepScan FTIR. StepScan FTIR is a technique where you use a normal FTIR with your Michelson interferometer, but you stop your interferometer at each possible mirror position, and then you measure a time trace there. So like this, you can get rather high time resolution in the microsecond range. The drawback of this technique is that you have to repeat your measurement over and over again to get the full time-resolved spectral response. So here you see the STEP-scan FTIR measurement of this bacterial rhodopsin photocycle, and you can see that there are different spectra visible in the first 100 microsecond, then in 400 to 800 microsecond, or 5 to 7 milliseconds. But to produce this result, 20,000 experimental repetitions were necessary. Now, we first tried to do the exact same thing with the IRis-F1, and on the right-hand side, you see the measurement with the IRis-F1. You see we could nicely reproduce those spectra. You also see one thing, we have somewhat higher signals, and that is not just because we wanted to make our life easier. That is actually a feature of the instrument. We've discussed that before. Because of the high brightness of the laser, we could work with thicker samples and therefore also got stronger signals. But all the kinetics are, of course, the same. And you see, we could get this result in only 500 repetitions instead of 20,000 repetitions that were necessary with the FTIR. Well, 500 repetitions are nice, but of course we wanted to go to the limit, and we did the same measurement in a single shot. And here you can see the spectra that were measured with only one experimental repetition, and of course, they are somewhat more noisy than what you have seen before, but still you can see all the important features of those different states, and we could actually show that you can nicely follow the kinetics through those various states from one single shot. And with this, I think we have a rather proud result that we were probably the first people to see the kinetics, the microsecond kinetics of an optically active protein with only one green light excitation at the start. Okay, and with this, I'm at the end of this presentation. Before I let you ask some questions, I'd like to point at upcoming events. There's a bunch of conferences where we are going to be present, especially for the biospectroscopy community. I'd like to announce ECSBM, the European Conference on Spectroscopy of Biomolecules, which will be next month in Dublin. We will be present there with a booth, and I would be happy to meet you at our booth there. And now, of course, I'm yours for any open questions.
Thank you, Marcus, for this very interesting talk. So, as you already said, we're now open for question and answers. And actually, we do have some questions. Sunadita Paul wanted to know to basically clarify the time resolution. So, I missed the time resolution. Can you give some idea about the instrument response function?
Okay, the instrument response function, so it is given by the length of the interferogram that we need to retrieve our spectrum. So it can, in not too big of a range, but it can be varied a bit. So if you have those heterodyne beatings, actually what determines the duration that you need to retrieve your beating is the distance between adjacent lines. This is typically on the order of a few megahertz, which allows you to get your spectrum every 1 microsecond. We once pushed it actually in this very experiment here. So if you look at the citation of the analytical chemistry paper, which is also on our website, there you can see that we pushed it down to 320 nanoseconds. And I would say that is about the limit. You could go maybe a bit faster, but so reasonable time resolutions that you can achieve are in the hundreds of nanosecond range, and standard would be a few microseconds of time resolution.
Okay, so basically you get the entire spectrum in 1 microsecond. If you push the system a bit, maybe a bit less, but 1 microsecond is the...
Exactly.
Yeah.
So,
And there's no drop off or something. It's not like with a detector you get the correct amplitude. Or maybe that was the question about the response function. So you get the correct value at 1 microsecond, so you don't have a 3 dB cutoff or something at that frequency.
Yes, exactly. There's basically no correlation between adjacent measurement points.
Exactly. Very good. So another question we're having often when discussing about biospectroscopy applications is that you showed this very nice laser at 1650 for the Amide 1 band. And of course, that's one of the most important laser availabilities. However, there are other bands which are interesting. I'm thinking of 1730 or maybe also around 2000. Do you have something upcoming there?
Yes, actually we do. I think you refer to the carboxyl band at 1730 wave numbers. This is a wavelength which is requested rather often, and we are developing it. We have some good results already with lasers which are slightly offset. So we have lasers at about 1760 wave numbers, plus minus 30 wave numbers. We expect to have them exactly fitting to the carboxyl band in a few months. So in the months to come, those lasers should get available. And then you were also talking about shorter wavelengths, above 2000 wave numbers. That is for biospectroscopy people interesting because there can be some protein markers. So normal proteins don't absorb there. With protein markers, they typically absorb above 2000 wave numbers. And we are currently developing those wavelengths. It does get a bit more difficult at shorter wavelengths, but we will make them available in soon time.
Thank you. Another question on the time resolution that we have is how do you set the time delay for time resolved measurement?
The time delay, maybe let's go back to that slide which showed the different measurement modes. So what you typically do in a time resolved measurement is you have a continuous measurement, normally for 32 milliseconds or maybe for up to 250 milliseconds. So in this duration of 32 milliseconds, you get your complete spectrum every 1 microsecond. So we're talking about 32,000 spectra that you measure continuously each microsecond. And then the important point is that you, of course, synchronize your measurement with your experiment. So typically, you will have either some optical excitation or a different kind of excitation to your sample. And this one will be given as a trigger to the IRis-F1, and then it starts measuring at that trigger, or in most cases, it actually starts measuring a bit before that trigger, such that you can take the pre-trigger time as a background, and then you just continuously get your spectra up to the complete sample time, and then you can just take whatever time delay you're interested in from this measurement.
Yeah. So I think it was very nicely explained. If we look at the two applications, so what you said in the bacteriorhodopsin is the laser is the one which was the trigger, like when the neodymium laser excited the bacteriorhodopsin, and on the curing example was the moment the shutter opened for the UV of the UV lamps, and those two were possible to measure.
Yeah.
So another question from one of our attendees is from Florian. Actually, is you mentioned 1730. Can you measure also formaldehyde spectra of the max peak at 1746 carbonyl Q branch?
Yes, that can be done. As we said in the specs, most of our lasers cover more than 60 wave numbers. So that typically means center wavelengths plus minus 30 or a bit more than 30 wave numbers. So for the 1730 laser, that would mean it reaches from 1700 to 1760 and also nicely covers the formaldehyde peak. Or actually, we can already now measure that with the 1730-100 laser not available because we have those lasers at 1760, which also cover that branch.
Yeah, we have done some test measurement for a customer where we see very nicely the formaldehyde spectrum and can fit it very nicely in different applications, actually.
Yeah.
Yeah. So thank you also for this question. Are there any more questions? Doesn't seem so. In any case, we're always open to answer any question also directly addressed to us. So really don't contact us, and we will have a phone call with you and make sure that everything is clear. With this, I would like to thank Marcus once more for this very interesting and very nicely explained webinar. And also thank you all to follow.
Yes, and also thank you very much for your attendance. And well, please get in touch if you have any more questions or any ideas of what you want to measure.
Yeah. Thank you, and talk to you later.